Have you ever seen a busy system that appears to be working hard, but somehow no real progress is ever made on its important tasks? It can be quite a puzzle to observe. This kind of endless activity without accomplishment is often a sign of a specific concurrency problem. Livelocks lead to system starvation because threads or processes repeatedly change their state in response to other threads, preventing any of them from making forward progress. Imagine two people trying to cross a narrow bridge, each politely stepping aside for the other, only to find themselves endlessly yielding without either ever managing to cross. This is the essence of a livelock. The core mechanism behind livelock starvation is a continuous cycle of mutually responsive actions. Unlike a deadlock, where processes are permanently blocked waiting for resources, in a livelock, processes are active and consume system resources like CPU cycles. However, their actions are always reactive and self-canceling, leading to a state where work is continuously attempted but never completed. Each process detects a conflicting state and attempts to resolve it by modifying its own state, which in turn causes the other process to detect a new conflict and modify its state again. This endless dance keeps all participants busy but unproductive, effectively starving critical tasks of completion. To identify or mitigate livelocks, it is helpful to look for situations where system components are actively consuming resources but show no discernible progress over time. One practical approach involves designing protocols that introduce asymmetry or a priority mechanism. For example, when multiple processes contend for resources, one process could be designated to wait a random amount of time before retrying, or a specific process could be given a higher priority to proceed. This breaks the symmetrical yielding pattern. Another technique is to implement an aging mechanism where processes waiting for a long time eventually gain precedence, preventing them from being indefinitely starved. The concept of livelock highlights the importance of careful protocol design in concurrent systems. In networking, for instance, a packet might be repeatedly forwarded between two routers if both detect an error and try to send it back to the other, creating a forwarding loop. This is a network-level livelock. A key term here is fairness algorithms, which are often used to ensure that all processes eventually get a chance to make progress, even in the face of contention, by breaking these reactive cycles. Understanding livelocks helps us build more robust and efficient concurrent applications. By recognizing the pattern of active non-progress and applying strategies like priority rules or randomized backoff delays, you can ensure that your systems not only remain responsive, but also successfully complete their intended work, avoiding the subtle trap of continuous activity without meaningful outcome.
If this helps you fix faster, like, subscribe, and keep debugging with us.